Okay, this tutorial will be covering vapor pressure and volatility. So, um, in this picture here, we have a gas that's inside a bulb, and then we have a certain amount of this is actually would be mercury that's in this tubing, and then this switch allows the pressure inside here to try to push on this mercury column right here. So, first of all, Earth's atmosphere is pressing down, so atmospheric pressure is pressing down on this column, and then it's pushing this mercury this way, and then it's going up the tube this way. So in this bulb we have ethanol, which is has okay IMFs. It's not great. It's good enough to actually be a liquid at room temperature, but it's a very volatile liquid. So ethanol is it's kind of similar to rubbing alcohol. So if you open that and then you smell it, you'll definitely end up smelling some. It's kind of like a petroleum type of smell because it's a hydrocarbon. Um, and let's see. Here's the structure of ethanol. Okay, so as you can see, it has the OH here, and it could do some hydrogen bonding. But then this part right here is all nonpolar. So that's going to not necessarily really form like very good attractive forces on another ethanol molecule. So we have this molecule is like pretty vaporous substance, and other things you might be familiar with are like household chemicals like maybe like acetone or nail polish remover. If you open the cap, you're definitely going to smell that distinct nail polish remover smell. It's like that solvent type smell. So um, and in fact, if you leave the cap open of either rubbing alcohol or something like nail polish remover, if you leave the cap open, and if you leave it open for a day or two, you're actually going to lose much of the liquid, if not all of that liquid. And it's because the reason why you're losing some is because of this. Like some of those liquid molecules are converting into gas molecules and they're flying up into the surrounding air. So it says some molecules have fairly weak intermolecular forces and it can escape their liquid state. So what this picture is showing is like some ethanols are down here at the bottom. Typically, the ones at the top can escape the top. These are actually, and we'll show a population distribution. This has everything to do with the kinetic molecular theory and population distributions of molecules. You'll see that these have tend to have the higher kinetic energy. So it would be like these ones on the top. So the top molecules generally have a higher Ke than the rest of the population of molecules. I'll put POP and population. Um, so this device, what you're looking at, is actually going to measure what's called vapor pressure, and it's appropriate to measure this in a closed system. So if it, pretend if this were open, like the example I was mentioning with nail polish remover. If you open the cap, that's an open system. So it's not gonna all those molecules are just gonna escape, and you won't be able to actually measure what its vapor pressure is like. So we're gonna use this closed system here. Okay, and then traps, and then you'll see that on the next picture over here, on this side, you'll see some molecules will fly into the top. Okay, so some of these have escaped and become gas forms. So these are gas, and then these are liquid. And here's kind of like the technical definition. So vapor pressure means it's at equilibrium. Some molecules will leave the liquid at the same rate as molecules. So some molecules will leave here, and then some molecules will come back down to become liquid. So this will go on until there's an equal rate of molecules leaving into the gas phase as there are going back down to the liquid phase. So anyway, when you have pretty, fairly weak IMFs, you're going to get some pretty volatile chemicals. So the chemicals, you'll have some certain amount up here in this area. And then as you notice, if you notice on here, So if you compare this thing that's measuring it with what's over here, you'll see that the pressure inside here has resulted in a push down on this column when you compare it to here. So what's happening is the uh, the it's exerting some the vapor pressure, or we use this symbol P with the subscript VAP, is pushing on the atmospheric pressure, which is what's making this column go this way. And depending on how much it pushed it, let's say from here down to here, typically this what's in here is like mercury, millimeters of mercury, and there would be like some. If you're familiar from our gas unit, this is it's called a manometer, this device here. So depending on how far this got pushed down, you're able to read the millimeters of mercury of vapor pressure. So, and remember, a millimeter of mercury is actually a torr. So 760 millimeters of mercury is 760 torr. So those two units are equivalent. Okay, so a couple other interesting facts about vapor pressure and volatility. So another example you might be familiar with is gasoline. When you go to the gas station, and you'll see like if you spill some accidentally, and let's say like when you take the pump out of the car, out of the gas, um, out of the gas tank, and you spill some comes out of the nozzle, you might see a few drops like sitting on the like right outside the gas tank, and you'll notice that immediately those drops are going to form vapor. So it didn't necessarily boil. All it really means is octane has very weak IMFs. It's good enough to be a liquid, but just barely, like at room temperature. So, and if you consider the structure of octane, so we have it's a C8H 18, and so it would kind of be like if I drew the skeleton structure of it, it'd be 2, 3, 4, 5, 6, 7, 8. Okay, and then there would be carbons here, like that. So it's entirely nonpolar. These little dashes I'm making are where the hydrogens would be. It's entirely non-polar, but as you can see, it's very linear, and so its LDS would be like sort of decent. Okay, but they would still be, if you added it up, it would still be just barely in the medium range. So it's good enough to be a liquid, but just barely. So stuff like that are like tend to be like pungent. You could smell them. When they're exposed to room temperature, they evaporate like very readily, even though they have not yet reached their boiling point. And I'll explain that on a couple slides in on this tutorial where we'll look at the population distribution. Okay, so if you compare that with like just if keeping in the line of cars and chemicals that go in your car. So if you look at octane versus motor oil is many, many more carbons, so the LDFs for motor oil are going to be a lot stronger than octane. And then this obviously motor oil is not volatile at all, so it's in fact it's like very viscous. It's close to being a solid, in fact. So um, and another key point about vapor pressure and volatility, and I've been mentioning this so far, substances do not have to boil to become gases. It just some certain amount have to have good enough kinetic energy to overcome atmospheric pressure, and then those will go on to become gas, even though the whole sample is not necessarily boiling yet. Okay, so they just have to have semi-weak to weak intermolecular forces, so sure, IMFs here, which lead to higher vapor pressures. Okay, so this explains why puddles evaporate, very slowly, even though water is obviously not boiling. So the perfume industry, like when you spray perfume, when it's enclosed, it's a liquid. But however, when you spray it, it's like just a lot of those chemicals that have those floral scents or what have you. They're liquids, and as soon as they hit your skin and exposed to room temperature, they become vapor. And so that's why they don't last that long over the course of the day. If you spray it on in the morning, then it would dissipate throughout the day, and then close to like halfway through the day, most of those liquid molecules have become vapor, and you won't really smell too much of it anymore. So a smart perfume scientist might want to make the molecule have like a little have maybe have it dissolved in a solvent that keeps it in solution longer and maybe makes the rate of those molecules evaporate, maybe make the rate try to go a lot slower. So um, okay, and the food flavoring industry is interesting. Is interestingly uses volatile chemicals as well. So when you bite into stuff, those chemicals go through your nasal passageway and then up into this area of your sinus is called your olfactory system, and which is like a giant ball of nerves that kind of figures out what things are smelling like, and it kind of assigns a flavor to it, and then it sends that signal to your brain. So okay, so here's like the technical definition of a boiling point. So it's um, so evaporation at the surface is vapor pressure. So this first picture here, this is a picture of evaporation. So you'll see some of these, the blue colored ones here. Let's color these blue. So these blue colored ones here are from this liquid. Okay, they're coming from here. Okay, and we have two different gas molecules kind of like fighting each other. We have the vapor liquid, vapor from the liquid that's in this beaker versus Earth's atmospheric pressure. So O2, N2, and other gases in the Earth's atmosphere are exerting pressure back down on this liquid. So we see some evaporation by some of these molecules. So that's vapor pressure. Now, if we look at this picture over here, so if we look at this picture over here, we see that now there's enough heat on this liquid, so there's enough heat acting on this to cause these to overcome the atmospheric pressure that's holding it down. So this, by definition, is the boiling point. It occurs when the temperature is raised to a point where the vapor pressure is equal to or greater than the atmospheric pressure, and that is boiling point. So you can adjust when something will boil by adjusting the atmospheric pressure as well. So for example, if you're in Denver, you live close to a mile above sea level, there's a lot less pressure acting on, like, let's say you're going to make a bowl of soup and you want to get the water boiling. Well, you don't have to get it as hot because there's less pressure acting on that's pressing down on the surface of the liquid. So to be consistent, I want to color in these so that you guys realize it's color coded. So these gas molecules are what's causing atmospheric pressure. Okay, and then the blue ones are coded so that hopefully you're recognizing that these blue ones are from the actual liquid. Okay, so that's by definition what boiling point is. So it's, again, I'll repeat this, that it's the temperature at which the vapor pressure of the substance is equal to or greater, so equal to or greater than the atmospheric pressure. Okay, so it depends on a point we could make here, like kind of a conclusion point we can make, is there's a few things that the boiling point. So we've covered this a lot, actually. So boiling point depends on, intrinsically, it depends on the IMFs, okay, and the temperature that the liquid is at, and externally, you can control it by the atmospheric pressure. So I'll write PATM. Okay, so, and I think we have some points over here about vapor pressure and volatility. So molecules close to the surface are able to leave the liquid. Those exert pressure. And these are kind of like take-home points from the first slide that we had with the manometer. So, and then another point about equilibrium. between its substance's vapor and its own liquid. So this is equilibrium between a liquid and its own vapor. Okay, it's established in a closed system, so that's how you measure vapor pressure. And I'll write see the manometer picture from earlier. Okay. And so some conclusions that we can make are when you have low intermolecular forces, then you're going to have a higher vapor pressure and you'll have more evaporation. The reverse of this is also true. So if you have high intermolecular forces, so molecules that are really good at sticking to each other are not gonna have very much vapor, which obviously will make less vapor pressure, and then you'll have less evaporation. Okay. And so liquids that evaporate readily or have a high vapor pressure are referred to as volatile. Okay, so on our next slide we'll show so in summary, yeah, here's the summary. Okay, so in to explain like what exactly is giving rise to this vapor, even though it's not necessarily boiling, we have to look at the distribution. So this is also called, and in the AP course outline, in the six big ideas, they refer to this distribution as the Maxwell-Boltzmann distribution. And they refer to this several times in the AP outline. They refer to it when we cover gases and root mean square speed. They refer to it now when they describe vapor pressure. And they are going to refer to it in the course outline. They're going to refer back to it again when we get to kinetics. So catalysts. So vapor pressure increases as temperature increases, and we'll show a distribution curve to explain why. So so sketch this in your notebooks. Okay, and on our y-axis, this is number or population of molecules with a given kinetic energy. And over here we have kinetic energy. And so we'll have a curve. When something is kind of cold, we'll have a curve that looks like this. Okay, and some will go here. Okay, so this is a bar graph, and each bar is representing a population of molecules. Okay, and you'll see that um, so an average thermometer will measure the average kinetic energy, which would be somewhere around here. So this is the KE average, and this is what your thermometer will pick up on. The point of this whole slide really is this. These molecules, let's just say for example that right here is the cutoff point. So this is when the molecules have enough kinetic energy to overcome atmospheric pressure. Okay, and so this is what this represents is a small, so some small population of molecules has enough kinetic energy to beat atmospheric pressure. Okay, now if we heat this up, so as the title of the slide implies that the vapor pressure depends on temperature, if we heat this sample up, okay, then our distribution curve gets more spread out. So we don't have as many molecules traveling the same kinetic energy. So so that's what I mean by it gets this distribution curve gets more spread out. So and they don't get as high these bars here. Okay, I'm kind of losing my ability to draw these bars here, and I'm running out of space. So what happened is the average kinetic energy increased, but more importantly, in terms of vapor pressure, and what we're studying right now is more. So we'll see that the cutoff point remains the same. So this might still be the cutoff point. Okay, so this is the when Ke is enough to overcome PATM. So because we raised the temperature, so this is a low temperature, and this is an increase in temperature. Then since we spread out the distribution, since right here is all bunched up, and then now it got more spread out, what happened is we have a lot more population of molecules compared to over here that are able to have kinetic energy to overcome atmospheric pressure. So it still hasn't boiled, right? When it boils, it will be when the average, when this point reaches this cutoff point right here, then it will boil. It will, by definition, be boiling. Okay, so but when these, um, so but so we've increased the temperature, but it still hasn't boiled. So you're gonna see more and more vapor. So this is why, if you're looking at a pot of water on the stove and you're waiting for it to boil, you're gonna start to see some steam more and more and more, even though the water is not like rapidly boiling yet. So even as low as like 40 degrees Celsius or 50 degrees Celsius, you're going to start seeing steam, which is well before 100 degrees Celsius when the average kinetic energy has reached it. So the reason you're seeing that is some of these actually do have enough kinetic energy, so you're starting to see some steam a little bit early. Um, so that's we're gonna kind of end here, and stay tuned for the next tutorial. We'll be doing a practice problem because all of these topics, vapor pressure, temperature, and the enthalpy of vaporization, they're all related in one equation. So as you noticed, vapor pressure, temperature, and enthalpy of vaporization all have to do with a molecule's IMFs. So it makes sense that they all are related by a certain relationship. And I'll go over a little bit of a background, and then we'll be doing an example problem using that relationship.